Hi all, Matt here. Just recording another quick learning video to step you through how I go about selecting images, targets to image from the Wellington Astronomy Society Cretney Observatory Dome. I'm just going to run through a few of the basics today. This is a really could be a really extensive topic, and the hope is that more of you will help us select what we're going to be imaging going forwards, and this will be a way that you can get involved really easily into how we run our observatory at the Society. So I'll jump straight into it. I'll hopefully cover off a range of topics from how I select targets or have been selecting targets when we've been doing the testing, give you some things to look for, giving you some technical information, and we can provide the details that I talk about as we go through the video separately, so you don't need to make notes or take anything down, and we'll try and make it as easy as possible for you. Okay, so without any further ado, we'll get into it. So first of all, just want to talk a little bit about the equipment that we've got in the dome. And the purpose of this really is just to give you a feel for what you'll actually be controlling when you're using the equipment, but also to set up some things about what it is we're actually able to image and not image with the setup we've got. The size of the field of view, the amount of the night sky that we capture in any one frame, and just a little bit about the context. So this is our telescope. It's the Officina Stellari Refast 400. It's a 400mm 16-inch primary mirror that's in the back of the telescope over here, and then the secondary mirror at the front, 40 kilos as it says here. The key thing for this discussion about selecting targets is to understand the focal length of the instrument, which in this case is 1520 millimeters. So that's the distance the light travels internally, the optical path length of the instrument as the light comes in at the front, bounces off the primary, off the secondary, and then out the back into the camera that hangs out the back. As we're talking about the camera that we use is the QHY 600 Pro. It's a full frame mono cooled astro camera, and the key things to understand about this camera, and here's the details on the QHY website, are that it's a full frame sensor, so 36 millimeters, and so that affects the amount of sky we can capture at any moment. The only other piece of equipment that's kind of important to understand at this stage is that we have this Gemini focusing rotator. Now the center of this rotator here it moves in and out to focus the telescope. This sits on the back of the instrument, between the instrument and the camera. You can see an image here of how it sits on the back of a telescope, and the camera screws into this round aperture here, and moving it in and out focuses. But the important part of this conversation is we actually have the ability to remotely rotate the camera, so we can change the orientation of our chip relative to the sky, which means we can have a little bit more freedom as we select the framing that we want for our particular image. That will become an important as we go down the track. Some other things that we don't have, so we don't have a Barlow or an additional reducer on this telescope, so it's possible that we might add that in the future. A Barlow magnifies, zooms in further, and a reducer does the opposite of that, so it gives us a wider field of view. But for the purposes of what we'll be talking about in the remainder of this video, the important numbers are the full frame sensor, 35-36 millimeters on its longest dimension, and the 15-20 millimeter focal length of the instrument. Of course, the other option we have is to crop the image after we take the image, and we also have the ability to only use a part of the sensor if we want to zoom in further. So obviously we lose some data and we lose some resolution when we undertake that, but it is possible to get an amount of zoom either in post-process or actually at capture if we select just a region of interest. Okay, so the next kind of part of the conversation is really about how we collect data on the instrument that we have. So we get the best, very best images we're able on a calm, still night, obviously no clouds, with the instrument pointing straight up as close to the zenith as possible. And so that's because there's less atmosphere to look through, so there's less distortion, and it makes the images it gives a higher resolution, the tighter stars, more contrast between the bright and dark areas. So the closer we can get to imaging at the zenith, the better. The other key thing that you need to know is as the Earth rotates, the apparent position of any particular object changes. So its altitude changes through the night, and also it changes through different times of the year. So for any particular part of the sky that we wish to image, there is an optimum time of the night and an optimum time of the year to which to undertake that imaging. And each subsequent night, the timing of when that object reaches its highest altitude from our position changes, gets slightly earlier. So we might image over several nights, over a week, the same target, and each night it'll get slightly and slightly earlier when it reaches that zenith. So when it reaches the highest point of its path, that's important for us to understand as well, to actually plan in taking the image. And the time of year is really important, because there are some objects that are not available at all at this time of the year, but might be later in the year. And there are other objects that are only visible from the northern hemisphere, which are obviously off limits to us as well. So there's a proportion of the night sky. We've got lots of targets to go after. You'll see as we go through this video, lots of opportunities to look at different things. So for the Cretney, what we're trying to do is image for a reasonable duration of the night. So what we do is we take a series of short exposures and then we overlay them and stack them and build up data that way, and that gives us a higher quality image at the end and enables us to see really faint details in the night sky. And so we're typically imaging for many, many hours and on a particular night, and then many nights, and then aggregating that all together. The latest image we've just been working on is about 45 hours worth of data, taking over around somewhere between 8 and 9 nights, and that's obviously weather dependent. And so that's kind of what the name of the game is. It's to try and image the particular target when it's as high as possible for as long as possible to gather as much data as possible. For the Cretney, typically we're trying to image things above about 45 degrees. It's not possible for all targets, but an altitude of somewhere between 45 and 90 is about right. So we typically start taking the images when it reaches about 45 degrees, take it as it rises up to its highest point, which may or may not be 90, depending on the time of year and the particular target, and then track it down until it drops to 40 or maybe 45 degrees on the other side of its highest elevation of the evening. And capture as much data as possible through that window. It's possible we can image down to somewhere between 15 and 20 degrees in the Cretney before the bottom of the slot gets in the way, or the trees, or some of the surrounding things. We've got a really good view of nearly all of the night sky that's available to us. There's no other obstructions other than some fairly low trees. And down at that elevation we wouldn't want to be doing too much imaging anyway, because of that extra atmosphere that we're trying to look through. So so typically you're looking for a target above 45 degrees for a number of hours in a particular evening, so that we can get a good window of data, and then you probably want to look at the best time of year to find that target to give us the biggest window and the greatest elevation, and therefore the best image that we can practically take. So a good example would be Matariki, the Pleiades cluster of stars, famous for our public holiday, which is actually when it becomes visible in the early morning sky. But actually, the best time of year to photograph that particular constellation is it's somewhere in December, January time. That's when it's actually highest, and even then, it's actually a very low target in the southern hemisphere from our location. So it's actually quite tricky to image. So we wouldn't want to be imaging it in June, July, August time. We'd be much better off imaging it in December and January. And so what we intend to do with the Cretney is line up a whole series of targets, but then actually go after acquiring that data and processing that data at the best time of year to get the best image we can. I'm going to show you some tools now that I use to help pick those best time of the year and to find some targets. I'll just start off by showing you a resource. There's lots of types of target that we can go after, and hundreds and hundreds of different things we can take images of. This is a particular resource called the IMM Deep Sky Companion. There's an Excel spreadsheet that goes with this. Here's some images of a fabulous array of different targets available in the night sky. You can see different galaxies, different nebula. We've obviously got the moons and the planets, globular clusters of stars. We can look at comets, potentially satellites and asteroids. Heaps of different types of nebula, from emission nebula, dark and reflection nebulas, and planetary nebulas, lots of different types. What's important for us, as I say, is understanding that kind of size in the field and how much they'll fill the frame. So we'll look a little bit more about the results of combining our particular choice of equipment and how much of the sky we can see, and then we'll have a look at how we might select some of these targets. But I guess the key thing I just wanted to draw your attention to here is lots of good information. This is one. We'll look at a few other tools, other websites and stuff that I use, but a lot of the targets that we might be looking at have been catalogued, and there's a Messier catalogue, a Colwell catalogue, Able catalogue, etc, etc, etc. And so a whole series of different ways of finding these particular targets. And then in this particular compendium, you can also look on Astrobin at some of the images, but there's a list of some images, so you can scroll through and take a look at some of these particular images, and then there are lists of the object's name and some descriptions about it. Yeah, its position in the night sky when it transits, so that's probably the best time of year to be looking to take images of it, so that's really useful. And its size is another important factor. We'll talk a little bit about size. That's probably a good segue to move into talking about our equipment that we have and the amount of the sky that we can actually image. So here's a field of view calculator. It just helps us kind of understand how much sky we can see. What I'm going to do is turn on a part of the sky that you'll be very familiar with, so the moon. We put in our focal length of our instrument, which is 1520 millimeters, you'll recall from earlier. Put it into imaging mode. And then if we select our camera, these are actually listed, so we can go down to the QHY 600 camera, which is our camera, and we're able to select our camera there, and then add that to the view. And this here shows the size that the full moon would be in our field of view for our instrument at Cretney. You can also do this for a range of other objects that you might be interested in. Not all of the objects, but for instance, you might be familiar with something like M42, so you could see how much of the M42 nebula you would be able to capture in a single kind of frame on our instrument. So this is really useful. What it tells us here is it tells us that we can get about 1.36 by 0.91 degrees of the night sky. The numbers in the table in the IMM compendium were in probably arc minutes, I would suggest. So yeah, we need to convert between degrees and arc minutes if we want to use that. But yeah, that's a useful resource. I want to show you another way of how I actually go about this, which is useful as well. The other thing I'd just suggest here as well, might be worth having a look at, is for our particular setup, imaging of planets is not ideal. We've got quite a wide field of view, wider than the moon, and the planets appear very, very small on our sensor. So when we get the Gifford Observatory up and running, we'll have a much longer focal length instrument, a smaller chip, and that will give us a much smaller field of view, and we'll be able to take photographs of the planets. The setup that we've got at the moment is not ideal for that. So things we can't take images of, so the sun, we don't have the right filters and we damage the equipment. Planets are probably too small, and then things that move very fast, satellites, asteroids, the space station, it is possible and our mount will keep up with it, but it has to be planned quite carefully, and the dome is probably limited by how fast the dome actually slews to be able to keep up with the telescope. So fast-moving objects might be a little bit tricky for us as well, but that leaves lots open to us. As I say, galaxies, nebula, globular clusters, comets that aren't too big, And so the other option, if things get too big rather than too small, is we can think about taking a mosaic, so overlapping several images to take an image of a larger part of the sky. So that's obviously very doable. It's more time consuming and it's more tricky to process, but it's possible to take larger areas of the sky. But very small portions of the sky are a little bit more problematic. Okay, so let's carry on. Let's look at the way that I typically would find a new target. So I use a website called Telescopius. It's a good catalogue of lots of different targets, potential targets. It has a series of latest astronomy kind of feeds that come up. It has some weather information, other bits and pieces. If you're going to use this for the Cretney, make sure you use about the right Latin long so that you have targets that are relevant to the night sky above Wellington. You can change the observing date if you want to look at different dates, and then you can come and select the type of thing that you might be interested in taking an image of. We've been looking at dark and reflection nebulas recently. I find them quite interesting personally, but you can look at other types, so whether it's clusters or constellations or comets or planets. And then when you've found an object that you particularly like, we can use the built-in telescope simulator to work out what rotation we want to put on the camera to best frame the subjects. We can work out a mosaic coordinates if we want to do that. And so what's really useful is you can have a look by popular targets or by brightest targets, or you can set up your own search, and we'll have a look at that right now. What I suggest you do is just get kind of familiar with this sort of software interface of finding new things to take images of. So here's all the things that are in the night sky tonight. What we're looking at here is the altitude that the object will follow through time, and then in the background you've got sunset and sunrise, and so we can see for the M42 nebula, it reaches the highest point in the sky tonight around about sunset, around about 21:50-ish. We can find out the exact time and date elsewhere, but this would give us an indication of its rise and fall. And if we're interested in this particular subject, we can click in here